Okay. Hello.
Hey, Roman.
Yes.
Hi, Roman. Yeah. Hi, David.
Hi, George.
Hi.
So, so we should wait for until 4:35 or something.
I think that's a nice idea. There's only 55 people here, and we never start the seminar with fewer than 60. Everything is different.
Right.
I think this might mean that in the future that maybe people will prefer this seminar instead of the other one. No? This kind of Zoom. Huh?
So it will be hard to move back offline.
I don't know. I mean, it seems like a nice thing to have access to a wider variety of seminars. All right, I'm going to just announce the next 2 weeks. In next week on April 29th, Lucas Mason Brown will give his thesis defense. The title is Unipotent Representations of Real Reductive Groups. In 2 weeks, Clifton Cunningham of the University of Calgary will talk about Arthur packets for G2 and perverse sheaves on cubics. And well, in 3 weeks, Jeffrey Adams will talk on a topic not yet settled. So today, I'm very happy that we have Roman Bezrukavnikov from MIT. And actually, it's the first in a few weeks that we've had a talk practically at MIT. Just at any rate, he's going to talk about canonical bases and coherent sheaves. So Roman, thank you.
Okay, thank you. And thank you for the opportunity to give this talk. I actually am not teaching this term, so it's my first Zoom presentation. So we'll see how it goes. And yes, I'm also want to thank my wife for providing help with devices and file editing and things like that. And it's not exactly my first slides talk, but I'm not very experienced in that either. Okay, let's see how it goes. So yeah, the title is all printed neatly, but that's deceptive. It's not going to be that way from my point on. Okay, so what are we going to talk about? So this is the main thing I want to discuss is canonical bases in the Grothendieck groups of coherent sheaves, varieties relevant for representation theory. But I will start with brief overview of the classical Kazhdan-Lustig theory. That's I guess one of the first places where this idea appeared. So Kazhdan-Lustig theory was devised to compute the characters of irreducible highest weight modules over semi-simple complex Lie algebra. So here I'm just recording the setup. So we have a semi-simple complex Lie algebra.
Actually, Roman, if I could ask, are you going to be kind enough to provide these slides so that I can post them on the that's yeah. Thank you.
Yes. Okay, so we have this complex semi-simple Lie algebra, something like SLNC on E8. And we have Verma modules, just modules induced from the upper triangular subalgebra, RL. And it's easy to compute their characters. And each such module is known to have unique irreducible quotient. That's the irreducible module with that highest weight. And everybody wants to know their characters. And thanks to this Kazdanovsky theory, one kind of knows that. And so let's recall how this goes. Yeah, okay, so just saying that we want to compute those characters. So how do we do that? I mean, how does Kazdanovsky theory do that for us? So let's put ourselves in a categorical context. So we consider the category where generated by these irreducibles. When I say generated, I mean just by extensions, category of finite length modules where all irreducibles are from this class. So that's category O. And just for concreteness, let's focus on the principal block, the block containing the trivial representation. So that I write that this contains C, the trivial representation. And all the reducibles have the highest weight in the dot orbit of 0. So dot action is just the action centered at minus rho. Yeah, so just a technical detail that I want to consider the abelian category of modules with diagonalizable Cartan action for now. Okay. So, and the Grothendieck group of this category is just the group ring of the Weil group. And the isomorphism I want to choose is I sent W to the class of the first appropriate Verma module with highest weight W dot minus 2 rho. Okay, and then so then computing the characters is basically equivalent to describing the image of the classes of irreducibles under that isomorphism, and the answer is that this is given by canonical basis, by the canonical basis, or Kazdanovsky basis. Whose definition I will not recall. I will instead recall the features of the theory that will be most relevant for me. So yes, so these are Kazdanovsky conjectures proved by these people around 1980. Yes, so I want to recall the key features. So, well, first feature is that this is related to geometry. And the proofs, well, until recently, all proofs were based on that connection. So the geometry is that of D modules of reverse sheaves. So that particular version of the category that I introduced is equivalent to the category of D modules, which are equivariant with respect to the Borel subgroup, upper triangular matrices, on not exactly the flag variety, but the slightly bigger space G mod U, where U is the radical of Borel of the group of, for SLN, this is the group of upper triangular matrices with ones on diagonal. I mean, I'm going through such details quickly, but I think that's appropriate, hopefully. Okay, so another feature which is maybe not strictly necessary, but I think it clarifies a lot. It's the relation. I mean, there is another category of representation of theoretic nature, which is actually equivalent to this category, and one who can rephrase, you know, all that kind of information about one in terms of the other. And this is the category of Harishchandra bimodules. So it's written here. Maybe I'll do it this way. So nice. Yeah. It's written here on the last line, category of bimodules of enveloping algebra, which are integrable with respect to diagonal action. And this indices here, 0 and 0 hat, means that the center of the enveloping of the left copy acts through this quotient. It kills the maximal ideal of the center corresponding to trivial representation. And for the second copy, it's a similar but different condition, namely this ideal should act nilpotently. And in terms of this can be proved, this equivalence of category order that with that Harishchandra thing can be proved directly, but it becomes very transparent geometrically because localization connects it to this thing. G equivalent modules on this product of these two spaces, and that's the same as the category we just talked about. But okay, so this is good, but that's certainly not good enough to give a proof of the of those conjectures. So I mean, the other important features, they have to do with the symmetries of this category. I mean, we said that this is the Grothendieck group of the Weil group, but well, the Weil group is a group in particular. It acts on this group algebra on this space of functions on it, but in fact, it acts from two sides. And so this action can be categorified, as people say these days. So the category carries an action, or two actually commuting actions of the art and braid group. And one can also introduce them algebraically. I will not talk about that, but the most transparent way is using these correspondences like Rodin transforms. I'm a little bit vague here, but I did not write down completely the definition of the functor, but it comes from this diagram. So you have G mod. In this localization equivalence, we see G mod B appearing. And so for this D modules or constructible sheaves, we have this formalism which allows one to pull back and pull forward things. And so if I have a correspondence between two varieties, then I have a functor from the category for one variety to the category for the other variety. And here the relevant correspondence, in other words, something mapping to both, is just the orbit of G on the square, and such orbits are indexed by the Weil group. And so for each element of the Weil group, we get a functor, and these functors generate the action. Sorry, so this is not, oops, I'm not sure what happened. Sorry. Yes, okay, so now, yes, this is the relevant slide. So another related symmetry of the category is the wall crossing functor. So there are these translation functors going between different blocks. And again, I don't go into much detail, but maybe say verbally that this functor, which one gets if one multiplies by a finite dimensional representation and takes the summand in the corresponding block. And so if one composes two such things, then one gets the wall crossing functor. And the notation psi is my idiosyncratic notation. I think nobody else uses it. I like it because it's psi is the way that Benson denotes maximal extension of a perverse sheaf, and that's related to that. But yes, so the main property of this functor is that it's exact self-enjoined, and in particular in sense projective objects to projective objects. And then there is another class of functors called Zuckerman functions, and again which commute with the wall crossing functors. So in terms of this localization thing, we should think of wall crossing functors as acting on the right, the way I wrote it, and the Zuckerman functors acting on the left. So yes, so these just come from, I mentioned that these T modules have the obey this 6 functors formalism, so you can push forward and pull back. And so in particular, for G mod B, we can just have the standard thing where G mod B is the flag variety, and say for SLN, we can just omit one space in this flag. And this gives me P1 vibration. And again, so this is just the fastest way to introduce them, but one can also define them algebraically using representation theory. But so these functors, their key property is that these are semi-simple. In other words, they send a simple module into a sum of simple modules, perhaps shifted sitting in different homological degrees. And this fact is deep and uses geometry, and in fact, just from this fact, one can deduce Kazdan-Lustig conjectures by pure algebraic means. Oh, sorry, it's something is wrong with my slides, but hopefully, yes. So this is the relevant slide, which says that the irreducible modules are, I just said that the function is irreducible, and adding just a little bit, I can say that the irreducible modules are up to homological shifts are exactly the summands of the result of application of the functors. So I didn't write that down, but what I mean here is that I take all possible sequences of simple roots, and for the Zuckerman functors index by simple roots, and for each sequence, I just compose these functors and I apply it to the irreducible Verma. They take all possible summands and I get all these irreducibles. And similarly, in decomposable projectives are summands of the result of application of those functors, or crossing functors, to the big Verma, to the projective Verma. And these classes give canonical basis and dual canonical basis respectively. There is also a version of this story where one does kind of a similar thing, but it just takes the sequences of Xis, but now applies it not to the big Verma, but to the reducible Verma. And then the summons are tilting objects. And so this is, also gives a version of canonical basis. I don't know, this term is maybe not very, I just made it up and it's maybe not very good, but it differs from the dual canonical basis just by an action of an invertible element, W0, so maybe it doesn't need a separate name, but I would like to mention that. And yes, and so one last feature to mention is that there is this famous causal duality of Benson, Ginsburg, and Zerg. This particular equivalence is due to Zerg, but Benson and Ginsburg also contributed a lot to this subject. And so, which is an out equivalence of the a graded version of this category, derived, of the derived category of the graded version of this category, where which interchanges irreducible and projectives. And maybe if I have time in the end, I will mention ingredients going into the proofs. And yes, and so what I want to also point out that there is a variant which is perhaps better in some respects, which interchanges irreducibles with tiltings. It's better in the sense that it's compatible with convolution, categorifying the algebra structure on the group ring of W. Any questions here?
Can you, what is the subscript on your or superscript on your category O?
0.
Sorry, superscript, not subscript.
Oh, yes. So this is just in this formula, not anywhere else. So it's a GR, meaning graded.
Thanks.
Any other questions? Okay, so now I'm getting closer to more recent stuff. So we were talking about D modules, and I didn't recall what they are, but they're modules over D, and D is the quantization of the cotangent bundle. So maybe we can get more classical and just dequantize things and look at the commutative algebra of functions on the cotangent bundle. And modules over that will be coherent sheaves. So here I'm just fixing the notation for the n tilde is the cotangent bundle to the flag variety. So I will now talk about canonical basis in the Grothendieck group. So yes, K is again stands for Grothendieck group. Canonical basis in the Grothendieck group of G equivariant coherent sheaves on the cotangent bundle. So I sort of sticking to the same structure. I started with representation of theoretical motivation. So this is also relevant to representation theory. Namely that canonical basis, it controls some, well, maybe more recent, gives answers more recent, but well, not very recent questions of representation theory. Namely, it controls the characters of tilting modules for quantum groups at root of unity. But so what I want to say next is that this is somehow supposed to be convincing you that it's not just the basis that's interesting, but there will be some, this basis consists of classes of some specific objects, and these objects are interesting themselves. And what I'm saying here is that these objects essentially are or contain information about cohomology of a small quantum group or its upper triangular Borel subalgebra with coefficients in a tilting module. And again, I'm just naming this, so if someone is interested, I can say a little bit more answering questions, but well, let me just mention this. And it's also relates, controls characters of some modules over the affine Lie algebra. So Kac-Moody affine Lie algebra constructed from the Langlands dual Lie algebra G. So that's the kind of problem it solves. But now, what about the construction? So I will, again, I will not talk about the actual definition so much, but I will present a characterization which is parallel to what we had before for the flag variety. So we said there that there are these irreducibles, and they are direct, after shift, they are direct summons in some explicit, more or less explicit thing that one gets applying, known functors to a specific generating object. So, but to run this procedure, I need to first introduce, corresponding symmetries of the category. So here again, there is a, there's this principle that dequantizing is like adding a loop. So you get an affine version of things. And indeed, here we have the action of the extended fine break group. So this is a, well, maybe the difference between extended and non-extended is minor, but then I can just say that it's argent break group constructed from the fine Dynkin graph, well, actually of the dual algebra. Yes, but it actually has a different set of generators, namely it has generators, it has a copy of the lattice. I mean, for SLN, I didn't write it down, but maybe let me say it. So for SLN, one can think of this as just fundamental group of the space of configuration of n points on C star, where you require that the product of all these points is 1. And then there are this lattice where you let just points run on each point run on its own circle. So I can make a drawing just for entertainment. So there's C star. So I throw out a point, and then there are many running points, and you can run on different circles. Well, I mean, you want to keep the product, but so the fundamental group of, you know, the classes of such paths generate z to the n-1, because there's like a copy of z for each circle, but then you want a total winding number to be 0, so it's z to the n-1. Anyway, so so it has these generators, and now I can just say how the generators act, and namely, it's actually easier to say how these lattice generators act, and they just twist by the corresponding line bundle. So they index by weight, by the weight lattice. So here it was zn-1. So I can just say, in terms of the previous example, so lambda SLN is the zn-1. Yes, so it's yeah, this lattice just acts by twists, and the simple generators corresponding to the fine to actually fine and simple roots act by very you know very explicit correspondence. So you have it's just have a reducible subvariety in the square. Yes, it has subscheme in the square, reduced subscheme in the square, consisting of the two components, namely diagonal and the core normal to the next orbit. So there is a orbits on this G mod B square where and bijection with W, and we take the orbit corresponding to the simple reflection, and we just take the union of these two things, and then we do again pull push for coherent sheaves. There's maybe some conjugation with minus rho twist, which I will not. Well, it's actually not. If you just want to define the action of the fine break group, it doesn't matter, because it's just conjugation. But then, for it to be compatible with other things, it has to be done properly. But I'm not being careful about that for now. There is also there are also the alpha, which will play the role of Zuckerman functions. And these are again, it's the same. It's again given by an explicit correspondence. You just take one of those two components. So n alpha again on the previous slide, and alpha was core normal to G mod B square S alpha, and maybe I should say the closure. You don't want to. Maybe I'll just write it this way so that it doesn't. Okay. Right, and then one needs to, it's actually very important for this construction to work, to define this not just for simple affine roots, but for all vertices of the affine linking graph. But fortunately, we can use this trick once we already know how the affine break group acts. Then these things somehow attach to simple reflections. So in the extended affine break group, one can always conjugate a simple reflection, a fine simple reflection to one of the finite ones, and then conjugating it back, you get the conjugating the corresponding Zuckerman functor, you get the Zuckerman functor corresponding to alpha 0. Okay, so and now I can state a theorem that I can again just start with the structure shift or, and again apply compositions of these things for every sequence of simple roots. But again, sorry, all sequence of vertices of the affine linking graph. That's very important. And then taking the composable summons and up to science, they will exactly produce the elements of the canonical basis. And again, there is a way to pick up, to make them well defined, not just up to a shift, but unambiguously. And then these things will be reducibles in some abelian subcategory sitting in inside this category of coherent sheaves. And so this will be heart of some T structure. And again, I already talked about their relevance. So they, for example, they contain information about this cohomology of the small quantum coefficients and tilting modules. What about, yes, so now I want to just demystify, and I don't have time to go into full detail of the definition, but just what do I mean by what do I mean by this thing being canonical basis element? I already said that this Grothendieck group is acted upon by the affine while group. And so here there is a typo because I forgot C star here, but I mean, I'm again throwing this under the rug, but of course, to set up this, maybe it's an appropriate place to just say a little bit about that. What I was saying was okay in the sense that, you know, it makes sense to talk about canonical basis in the group ring of the while group and say that it controls the characters, but to set it up, to define it and compute it, one needs to consider the Q deformation. So one have to work with Q deformation. And so here I just want to mention that. So we talked about the affine break group acting on the category, then on this Grothendieck group, we have an action of the affine while group, and then on this graded version where you add C star, you have an action of the affine Hicke algebra. And then this module is can be explicitly described as a induction of the sign from the finite Hicke algebra. So this is this tensor product is what's the thing at the bottom is the finite Hicke algebra, and this is a sign representation. And then the finite Hicke algebra has or its degeneration, they have canonical basis, which is constructed, in a pretty similar way to canonical basis in just ordinary Hicke algebra. And then, so this is this induced module. It's a cyclic module. In particular, it's in particular, it has a since it's written as a tensor product, it certainly gets a canonical onto map from the algebra. And then the canonical basis in the algebra just produces canonical basis in the module. Just some elements under the surjection, some elements will go to 0, and the others will give a canonical basis. So one can ask, I mean, is there a more complete parallel between this story and the previous story? Well, so first of all, okay, so we produce this basis in the Grothendieck group of the cotangent bundle from the canonical basis in the Hecke algebra is degeneration. So can we also give a geometric construction for the basis in the Hecke algebra itself? And is there a more complete parallel with the previous story, or can we account for the dual canonical basis? Okay, so these are rhetorical questions. So the answer is yes. To set this up, we need to say that according to Lustig and then Ginzburg and Lustig, so we can realize. So again, I wrote here the degenerate version. There is no Q, but there is also, of course, version with Q. So we can realize it as a Grothendieck group of this Steinberg variety. Square fiber of a cotangent bundle over the Lie algebra, and then one can construct. And then again, one can one can introduce this function Z alpha. There is no, I didn't write this down, but it's just basically the same correspondence. In fact, there's also left and right version, and we only need one here, say left. So we just do the same correspondence we did before, but along one copy. And then we get again the BFI action and also Z alpha. I mean, this what I call Zuckerman functions. And then again, I'm just saying the same formalism applies. So you can take direct summons of these things where you apply it many times and take direct summons, indecomposable direct summons, and this there is a way to normalize the shift, but so it's exactly the same thing. So they're irreducibles in the heart of some T structure related to category O for the affine algebra, and well, I inserted some advertising for work in progress with Simon. So it's related to Chandra bimodules and positive characteristic or quantum group. This is related also to the recent conjecture of Denis Kaiskari, but this is a side remark. But so what's important here is that, you know, if you were taking what I said too literally, then it's too bad. So I actually lied in the sense that this all works. I mean, only if we consider this fiber product as derived scheme. So the thing is that when by definition, functions on this fiber product is a tensor product of the rings of functions over the ring of functions on the base. And when you compute this tensor product, you discover there are high tors. And somehow if you discard them, as you do if you just write this naively, then you just don't, then this just doesn't work. I mean, it does not affect the Grothendieck group. So you're still okay in terms of realizing the Hecke algebra is some K group, but these constructions just don't work. And so, well, is there a way around this? Perhaps, you know, perhaps someone in the audience doesn't like derived schemes. Can he or she still do something here that they like? And And that is yes. And also another, yeah, this will also bring us to a setting where we'll be able to do the dual canonical basis. So the thing is that along with N-tilde, there is this G-tilde. So this Grothendieck simultaneous resolution. So I think, you know, people know that G-tilde is a set of. So I think of the flag variety as a variety of barrels, and then it's just this sort of thing. So the difference with N-tilde is that in N-tilde I would have to require that X lies in the radical of N. So for SLN that it strictly preserves the flag, sending VI to VI minus 1. And here I just wanted to preserve the flag and send VI to VI. And the Grothendieck group is actually exactly the same. So, but the game one can play is somewhat different. So somehow here I'm saying that we will have not the analog of Zuckerman functors, but only the analog of the crossing functors. And these are just push-pull for certain natural correspondence. I didn't write what G tilde alpha is, but that's defined in a very similarly. So G tilde alpha is the set of pairs. Now we have like P, so there's P alpha in now in G mod P alpha. So I have taken minimal parabolic of corresponding to the given simple root. And then, so again, for SLN, I just take incomplete flag, but I skip one dimension, and then I consider things which are block up triangular with respect to the corresponding flag. And so, yeah, so there is this map which is generically 2 to 1, and then some fibers are double points and some fibers are projective lines, and they just take push-pull. So that's kind of, so that turns out to be an analog in precise way of the crossing functors. And then again, I can just do the same game, play the same game, and I take the apply these functors and take the all indecomposable summons. So here, ambiguity, I will actually not have ambiguity with homological shift. I will have ambiguity with, I would have ambiguity with C star action if I wrote C star there. If I'm considering the, if I'm not including C star in the game, then there is no ambiguity. So I just take all summons and I claim that this is this form like a dual canonical basis here in some sense. And so these are analogs of tilting modules. Yes, so well, I'm saying they will provide a basis in the Grothendieck group, but there is also a more like algebraic categorical statement, namely that the homotopic category just maps to the category. So here, G, to our category, I mean, by nuclear. And so this actually is related, so this will appear on a later slide, but this is related to this property that higher X, this is supposed to be curly T, not J, but if you want to think it's J, it's also okay. So yes, so the properties that we need is that this is equal to 0 for T1, T2 in this thing, and also that they generate the category in some strong sense. So it's the whole category. So this is basically a restatement of. Yes, and so now the question is, what is? So it turns out that these two settings that I talked about, they are related. And they're related by this linear causal duality of Merkovich-Risch, which is inspired, I mean, a similar construction to this Belanger-Ginzburg-Zergel in this context. Maybe it's a good place to ask for questions. So, are there any questions? No? Okay, so yes, I'll briefly recall. I mean, this linear causal duality, it's just some sort of generalization of the very basic example of causal duality, which, you know, if I think everyone who has heard anything about causal duality should have heard that the exterior and the symmetric algebra are dual in this sense, because X from K to K over the exterior algebra is symmetric algebra and vice versa. But here there is an yet another point that this so again, so lambda v and sim v star are dual in that sense. That again, sim x from K to K over lambda v is the sim v star. And vice versa. So, but if you take X over symmetric algebra, you get lambda. But here I also want to think of lambda as the Tor algebra over sim v from K to K. And you know, this Tor algebra is exactly what you know, people have to work with if they consider if they move into this derived geometry territory. So this is a, in this fancy language, this Tor algebra is functions on the derived self-intersection of 0 over v star over. So this is like functions on point times point over spectrum of sim v, which is v star. And okay, so one can basically put this over the base, and then one discover this pretty formalism. So this is what Ivan and Simon Risch did. So over the base, maybe you can generalize, but I like this picture. If you take a vector bundle and have two subbundles, then you can take just their fiber product, the intersection, just over the total spaces. Then if you have a vector bundle, you can dualize it, of course. And then if you have, for the two subbundles, you have the two orthogonals. And there is this causal duality relation between coherent sheaves on the two intersections. And again, these intersections can be understood as derived schemes, but there are interesting examples where there are no higher torso, and then they can be understood in the good old classical way. And so it's relevant to us here because we are exactly in this station. So we can take the base to be the square of the flag variety. So that's an example. We take the base to be the square of the flag variety. So we take the trivial bundle with fiber G, and this is self-dual. And then we can take like a sub-bundle where we require to strictly preserve the first flag, or we can ask it to strictly preserve the second flag, and then the intersection would be exactly the thing that we just considered before. But when we take orthogonals, then there's a standard observation that orthogonal to strictly upper triangular matrices is just upper triangular matrices. And so we get the orthogonals are exactly the second setting. And then one can check that the what I call, I mean, Z alphas, I didn't write this down, but under this equivalence, Z alphas are interchanged with psi alphas. So now, yes, and then all the diagonal is interchanged with all of the diagonal. In particular, these two bases are interchanged. And yes, so I didn't write this down, but one can compute the effect of these things on the growth intergroup, and this is Iwahori Matsumoto involution, so very easy to write down involution on the Hecke algebra, and okay, so so now I'm want to nearing the end of my talk, and I want to state some conjectures generalizing this to a different setting. To introduce the setting, I now want to equip my group with an involution and take let K to be the fixed point of this involution. And then we take the two subvarieties. So we can kind of do, again, a similar thing. We take intersection of two subbundles in the in a trivial vector bundle, actually. So one thing that people usually consider in this theory is this just the fiber product of n tilde with K perp with orthogonal to K. So this is another said differently, it's the union of core normals to K orbits on G mod B. And yes, I was going to mention this, but again, I motivated going to coherent sheaves by kind of dequantization. And so, yeah, this is what you get if you dequantize a K equivariant D module. So, yes, so I wanted to mention that so we can also take the intersection of the orthogonal subbundles in the dual bundle, which is also the same bundle, and then we just take points in G tilde, which where the element is required to lie in K. So this is some sort of fixed point variety. So you have a K is acting, and then we just take a pairs consisting of a point in the variety and an element in the algebra stabilizing it. There's a vague remark that maybe actually, yeah, I want to make a vague remark about relation to so it kind of resembles the relation between character cycle and characteristic cycle and character cycle proposed by Kashiwara in some setting proved by Schmidt-Villanin, but yeah, this is a vague analogy, so I don't want to go deep into it. But again, so these are two settings that are related by this linear causal duality, and so a remark, technical but important remark here, is that the thing on the left is a derived scheme, except in a very special case if theta is what called split. If it, well, these things correspond actually to real forms of G, and so if you start with the split real form, then theta will have this property that there is a theta stable Cartan where it just the space of invariance is 0. So this is a very, very special situation. However, the thing on the right is always a complete intersection, and so it's always a good, honest scheme. There are no high torsions, so you don't have to think about this derived stuff. And so, yes, just again, doing the same thing we did before on the left factor, just doing some formal base change, we can make functor Z alpha act on the left and psi alpha act on the right. And so now I can propose, a bold conjecture. It's not, well, okay. So it's a conjecture saying that if I take, so I wanted to put G to be a joint, just because I tried to do the calculation for SL2 and for PGL2, and I was getting confused with SL2 more. But hopefully hopefully it can account for, hopefully this is not necessary with, so what I want to do here is that I want to just take this, so as I explained, there is the right thing is kind of technically easier because you don't have to work with the right stuff. And so I just take the structure sheaf of the pre-image of the closed orbit. So it's isomorphic to K tilde, or G tilde for G being K. And then I apply all possible combinations of these functors and take direct summon. So I call this, consider the full subcategory, in this case in sheaves, and I call it TK. And then, yes, actually something I didn't write down, but which is important, that part of the conjectures that these are actually sheaves and not complexes. So that's something that's true again in the previous case. And so the categorical conjecture is that the homotopy category of that thing maps to our derived category by an equivalence, and then the classes from decomposables form, dual canonical bases, which can also then be transported to a canonical basis in the left-hand side. So yeah, so this seems to work for PGL2. And then there are other kind of. So yeah, so an important disclosure, if you like, is that in the complex case, so this proves based on comparing this coherent picture to the Langlands dual side, where one works with a fine flag variety of the dual group. And in the K tilde setting, I don't know such a realization, although there are conjectures by Bensley and Adler of this sort. And so remark 2 is just about a partial evidence that, yes, so as I mentioned in the previous setting, it's basically to properties, X vanishing and generation. And yes, I can check X vanishing for some, not all of this sheaves. And yes, and then, well, I'm basically out of time. But remark 3 is sort of another maybe technical advantage of the right side in working with this fixed point scheme rather than the union of conormals is that this category should have a nice Zerg bimodule style description. And so if I can take another 2 minutes, maybe I'll say a bit about that and then I'll stop. Is that okay? Okay, so basically Zerg bimodules method is some method to describe our category, which actually was initially introduced by Zerg exactly for the purpose of proving this causal duality. I just want to say that it's actually has a very transparent, more transparent than the original context, kind of place here. So recall that Zerg bimodules are just some full subcategory in well, that's actually also true, but I wanted to write it this way. So, so it's a bimodules of the polynomial algebra in Cartan, but the invariant part acts diagonally, so it's the same as union of graphs. And but to kind of relate it to our context, I just want to mention that, well, there is this constant slice, right? So the schema W, it embeds, can be embedded in the algebra as a slice, transversal slice to a set of nilpotent elements constructed by word constant. And but then if you so this actually lands into G reg, the regular part. And over this regular part, the map from G tilde to G is a ramified covering. And putting this all together, we see that if I just take the pre-image of schema W in this fiber product, which we considered before, I recover exactly the Jorgen thing. So I can just without any thinking, I can immediately define a functor to there from my category of sheaves on this thing, just restriction. So I call this constant thing kappa, and then I call this thing obtained from it by base change by kappa tilde, and then there is a you can just consider the pullback functor, and then there is a k version. It's just you take the Cartan of k, which I call tk, and again I take the corresponding fiber product, and it embeds into what I call k tilde. So this is just the same as k times u tilde. But this is not yet the thing we want, because here I mean, Zerg bimodules only allow one to compute to control the original category O. And but yes, actually one can use the picture that I just presented to kind of present yet another construction, which I like of Zerg's functor, where you pass from D modules to coherent sheaves by using Hodge filtration, and then one just restricts to the slice as I just did. But that's not my main point. My main point is that one can also introduce affine Zerg bimodules, and that will control our category well in the known case, and hopefully it also applies to the K case. Namely, well, so more to say about it, but so affine Zerg bimodules were considered by different people. In particular, Abe made this nice and convenient, introduces convenient way of thinking about them. Namely, it's a full subcategory in pairs. You take just a modulus before over this thing, and then you endow it with an additional grading. And I claim that our equivariant sheaves are exactly land here, namely, so this is the last thing I'm going to say. The point is that we can restrict to this preimage of the constant slice, but well, we get just a coherent sheaf there. We forget equivariance, but we don't have to forget equivariance. And if we remember how the centralize of an element or a regular element acts on the fiber, then we exactly get this additional grading that Abe is talking about. And then there is an obvious counterpart of this in this case setting, where you just well here, and yes, it's important that TK always hits regular elements in G. Okay, so then this last slide, I'm just saying that one can define this. So upgrading, I didn't write this down, but yes, the way I just said, and then one can write this in the K setting and hope that it's going to be also fully faithful on this category on our category TK. Okay, so I think it's a good place to stop.
Thank you. So
Any questions?
yeah, I wanted to ask, could you gave a little explanation of the left-hand side of your picture with K, this N tilde crossover G with K perp. You described that as the union of the conormal bundles to the
Right.
K orbits. Could you give a description like that for the right-hand side?
Yeah. So this is the this is something that you can consider, whenever you have a group acting on a variety. So it's a so if I replace so maybe I'll write it here. If I replace it, so G acting on X, I can consider this. Well, I of X, you can have a group and the algebra version. So it's a set of pairs consisting of X, G, such that G of X is X. Or you can have the Lie algebra version. So I don't know how to call it. It's IG, and then you have IG, the set of X, and then I don't know, A in G, so that A vanishes at X. So the corresponding vector field A maps to 0 in T X of X. So I think if you, so this is called, if you quotient this IG modulo G, then this is known as inertia stack. So in the stack language, it's just the fiber. It's X times G times X times G over X mod G squared. So it's a fiber square of diagonal, but you don't have to work with the stack language. So it's and yeah, so I not really prepared to explain in detail, but Kashiwara considered in particular introduced this notion of character cycle. The idea is that characters are something have to do with traces, but if you have like an element and a fixed point, then you can compute like a trace of a stalk, like of a covariant sheaf at that point, something like that. And so, so this is some sort of cycle in that, what I call IG, in the same way as singular support lies in, a characteristic cycle lies in the union of conormals. Any other questions?
So, so this K version of Zorgo by affine Zorgo by modules. Do they also have descriptions in a more traditional way by modules over to two copies of polynomial algebras?
In fact, I think here, I mean, I just said it this way for brevity, and I think this Abrams formalism is really crucial that if you work in characteristic P, which we don't do here. So here, I think it's, you can just talk about this affine Zerg bimodules in terms of coherent sheaves on the union of graphs of all elements in the affine well group.
Mm-hmm. Mm-hmm.
It's so it's not lit. It's closely related to that. I can explain maybe later. So it's
The K version.
So no. I'm first talking about the G version. So yes. So the G version is closely related to what I just said. It's not literally that, but it can be obtained from that by some affine blow up, which I can explain, and I have some notes. Some notes. So Georgie had this notes for like summer school he gave in some place 147 kilometers from Moscow, and then there is a short note on exactly this issue that I wrote for that school, but which is also on this website. So I'm thinking that, you know, I haven't thought much about it, but I'm thinking that in the K versions, you again can take just again union of graphs of all elements. So you have one embedding of K into of TK into T. And then you have a bunch of other embeddings. You just take this initial one and you apply all elements in the affine Weil group. And then you just can take the union of these graphs. So it's not a subscheme, but some in-scheme. And then you do this little renormalization, this affine blow up that one needs to. But essentially, I mean, in terms of it's like in our paper where, you know, we for the category that we started in this first case, that in the G tilde times G tilde case, this is, you know, closely related to this sheaves on affine flags, but it's not. It sheaves, you know, perhaps with some equivariance, but not with full equivariance because it doesn't include the loop rotation. So if you did include the loop rotation, then that would be literally union of, that would be the Kac-Moody setting, and that would be literally the union of graphs of elements in the affine Weil group. But I won't say it by our paper, but more or less by our paper. So here it's you have to do some modification because it's not exactly this full Kac-Moody equivariance, but one can do that.
Okay.
Any other questions?
So you said you didn't have a geometric realization in this case, but just for the Grothendieck group, do you have some interpretation in terms of the dual side?
That's a good question, but not really. I mean, I'm not saying it's probably doable, but I don't know. I mean, I think it's an interesting thing to work out. Yeah, the short answer is no. I expect that it can be done, but no, I don't know. So these conjectures, I mentioned this conjecture of Daller-Ben-Zvi, they involve some sheaves on the loop group, which are covariant into loops into the real group, something like that. And as actually George Lustig pointed out, there one can also work with a different setting where one can take loops into K, C. So yeah, it's kind of, it's clear where to look, but it's yeah, there are I think it doesn't look like an easy problem to really write down the categorical equivalence, but yes, analyzing the growth in the groups is maybe more accessible.
Thanks.
Okay, I'm gonna say thank you again, and we'll meet next week.
Thank you.